The National Electrical Code (NEC) and California Electrical Code (SEC) do not have a specific prohibition against polyvinyl chloride (PVC) conduit in schools. However, it is important to note that certain local codes or school district policies may have additional requirements or restrictions. The California Building Standards Code (CBSC) Section 1012.5(1), Title 24, Part 2 requires that electrical raceways installed in concealed spaces of schools be installed in accordance with Section 680.26 of the NEC. Section 680.26 of the NEC allows PVC conduit to be installed in concealed spaces of schools if it meets certain requirements. These requirements include: firstly, the conduit must be Schedule 80 PVC or equivalent. Secondly, the conduit must be securely supported and protected from physical damage. Thirdly, the conduit must not be used in areas where it may be exposed to high temperatures or corrosive substances. Some schools or school districts may also have specific policies against PVC conduit. For example, the Los Angeles Unified School District (LOSD) prohibits the use of PVC conduit in all wiring systems within schools due to concerns about fire safety and the release of toxic gases. The San Francisco Unified School District (SFUSD) restricts the use of PVC conduit to specific applications, such as where it is concealed in concrete or below grade. Looking at other states, the New York City Building Code (NEC) prohibits the use of PVC conduit in schools except in limited applications, for example, underground or where approved by the Commissioner. The Florida Building Code (FBC) allows PVC conduit to be used in schools if it meets the requirements of Section 300.5 of the NEC. Section 300.5 of the NEC covers underground installations. It specifies requirements for minimum cover depths, wiring methods, and protection against physical damage. In summary, while the NEC and CEC do not universally prohibit PVC conduit in schools, various local codes, school district policies, and state building codes may impose restrictions or specific requirements. It is always advisable to consult with the local building department and the school district to determine if there are any specific requirements or restrictions on the use of PVC conduit in schools. When installing electrical conduit, it's important to understand the different types available and their appropriate applications. PVC conduit is a popular choice due to its cost-effectiveness, ease of installation, and resistance to corrosion. However, its use is often restricted in certain environments due to concerns about fire safety and mechanical strength. Other common types of conduit include rigid metal conduit (RMC), intermediate metal conduit (IMC), electrical metallic tubing (EMT), and flexible metal conduit (FMC). Rigid metal conduit (RMC) is the heaviest and thickest walled conduit, providing excellent protection against physical damage and electromagnetic interference. It's typically made of steel or aluminum and is suitable for both indoor and outdoor applications, including direct burial and hazardous locations. Intermediate metal conduit (IMC) is lighter and thinner than RMC but still offers good protection. It's often used in similar applications as RMC but may be more cost-effective in some situations. The electrical metallic tubing (END) is a thin-walled conduit that is easy to bend and cut, making it a popular choice for indoor applications. It's not suitable for direct burial or hazardous locations but provides adequate protection for wiring in most commercial and residential settings. Flexible metal conduit (FMC) is a spiral wound conduit that allows for bending and flexing, making it ideal for connecting to motors, luminaires, and other equipment that may require movement or vibration. It's not suitable for wet locations or direct burial unless specifically listed for those applications. When selecting conduit, it's crucial to consider the environment in which it will be installed. Factors to consider include exposure to moisture, chemicals, extreme temperatures, and physical impact. The NEC provides detailed requirements for conduit selection and installation in Chapter 3, Wiring Methods and Materials. It specifies the types of conduit permitted in different locations and the requirements for supporting, grounding, and bonding the conduit system. In addition to the type of conduit, the size of the conduit is also important. The conduit must be large enough to accommodate the number and size of conductors being installed, while also allowing for future expansion. The NEC provides tables in Chapter 9 that specify the maximum number of conductors permitted and different sizes of conduit. When installing conduit, proper techniques are essential to ensure a safe and reliable electrical system. Conduit must be securely supported to prevent sagging and damage. The NEC specifies the maximum spacing between supports for different types and sizes of conduit. Conduit must also be properly grounded and bonded to provide a low impedance path for fault currents. This helps to protect against electric shock and reduce the risk of fire. The NEC provides detailed requirements for grounding and bonding in Article 250, Grounding and Bonding. In areas where the conduit may be exposed to physical damage, it should be protected by barriers, guards, or other means. This is especially important in industrial and commercial settings where the conduit may be struck by vehicles or equipment. In corrosive environments, such as those found in chemical plants or wastewater treatment facilities, special types of conduit and fittings may be required to prevent corrosion. These may include PVC-coated conduit, stainless steel conduit, or non-metallic conduit. When making connections to conduit, it's important to use the correct type of fittings. The fittings must be compatible with the type of conduit being used and must provide a watertight and dust-tight seal. In hazardous locations, special types of fittings are required to prevent the ignition of flammable gases or vapors. These fittings are designed to contain any explosion that may occur within the conduit system. When installing conduit in concrete, it's important to protect it from damage during the concrete pour. This can be done by wrapping the conduit with tape or using special conduit spacers. The concrete must also be properly consolidated around the conduit to prevent voids and ensure a good bond. In areas where the conduit may be exposed to extreme temperatures, expansion fittings may be required to allow for thermal expansion and contraction. These fittings prevent the conduit from buckling or cracking due to temperature changes. When installing conduit underground, it's important to follow the NEC requirements for burial depth. The minimum burial depth depends on the type of conduit, the voltage of the circuit, and the location of the installation. The conduit must also be protected from physical damage by a layer of sand or gravel. In summary, the selection and installation of electrical conduit are critical aspects of electrical safety. By understanding the different types of conduit, the NEC requirements, and proper installation techniques, electrical contractors can ensure a safe and reliable electrical system. Always consult with a qualified electrical inspector or engineer to ensure that the conduit installation meets all applicable codes and standards. Different types of conduits offer varying degrees of protection and are suitable for different applications. Understanding their properties is key to a safe installation. The information provided is intended as a general guide and should not be considered a substitute for professional advice. Always consult with a qualified electrician or engineer before undertaking any electrical work. Also, remember to always comply with the latest edition of the NEC and any applicable local codes and regulations. These codes are updated regularly to reflect the latest safety standards and best practices. By staying informed and following these guidelines, you can help to ensure a safe and reliable electrical system. Regarding conduit fill, which refers to the amount of space within a conduit occupied by conductors, it's crucial to adhere to the NEC guidelines to prevent overheating and ensure proper heat dissipation. Overfilled conduits can lead to conductor insulation breakdown and potentially hazardous situations. NEC Chapter 9, Table 1 provides the maximum percentage of conduit area that can be occupied by conductors. These percentages vary depending on the number of conductors in the conduit. For example, for one conductor, the maximum fill percentage is 53%, for two conductors, it's 31%, and for three or more conductors, it's 40%. To determine the required conduit size, you need to calculate the total cross-sectional area of all the conductors that will be installed in the conduit. This can be done by referring to NEC Chapter 9, Table 5, which provides the dimensions and cross-sectional areas of different types and sizes of conductors. Once you have the total conductor area, You can use NEC Chapter 9, Table 4 to determine the minimum conduit size that meets the fill requirements. Table 4 provides the usable area for different types and sizes of conduit. It's important to note that these tables are based on specific types of conductors and conduit. If you are using conductors or conduit that are not listed in these tables, you may need to consult with the manufacturer or a qualified electrical engineer to determine the appropriate fill requirements. In addition to the fill requirements, the NEC also specifies minimum bending radii for conduit. This is to prevent damage to the conductors during installation and to ensure that the conductors can be easily pulled through the conduit. The minimum bending radius depends on the type and size of conduit. The NEC provides tables in Chapter 9 that specify the minimum bending radii for different types of conduit. When bending conduit, it's important to use the correct tools and techniques. Avoid kinking or flattening the conduit, as this can damage the conductors and reduce the conduit's carrying capacity. Use a conduit bender that is designed for the specific type and size of conduit being used. When pulling conductors through conduit, it's important to use a lubricant to reduce friction and prevent damage to the insulation. Use a lubricant that is specifically designed for pulling electrical conductors. Avoid using petroleum-based lubricants, as these can damage the insulation. Pull the conductors smoothly and evenly to avoid snags or kinks. If you encounter resistance, stop pulling and investigate the cause. Do not force the conductors through the conduit, as this can damage the insulation. In some cases, it may be necessary to use a pulling rope or fish tape to pull the conductors through the conduit. These tools can help to guide the conductors and reduce friction. When using a pulling rope or fish tape, be sure to use a knot or connector that is strong enough to withstand the pulling force. Avoid using sharp or abrasive knots, as these can damage the conductors. After the conductors have been pulled through the conduit, inspect them carefully to ensure that they have not been damaged. Look for cuts, abrasions, or other signs of damage to the insulation. If you find any damage, replace the conductors before energizing the circuit. Remember that proper conduit fill, bending radii, and pulling techniques are essential for a safe and reliable electrical installation. Always consult with a qualified electrician or engineer before undertaking any electrical work. In addition to the requirements for conduit fill, bending radii, and pulling techniques, the NEC also specifies requirements for supporting and securing conduit. Conduit must be supported at intervals that prevent sagging or damage. The NEC provides tables in Chapter 3 that specify the maximum support spacing for different types and sizes of conduit. The support spacing depends on the type of conduit, the size of the conduit, and the location of the installation. In general, conduit should be supported at intervals of no more than 10 feet for rigid metal conduit, RMC, and intermediate metal conduit, IMC, and at intervals of no more than 3 feet for electrical metallic tubing, EMT, and flexible metal conduit, FMC. In addition to the support spacing requirements, the NEC also specifies requirements for the type of supports that must be used. The supports must be designed to securely hold the conduit in place and must be made of materials that are compatible with the conduit. Avoid using supports that can damage the conduit or cause it to corrode. When installing conduit in wet locations, it's important to use watertight supports and fittings. This will prevent water from entering the conduit and damaging the conductors. Use supports and fittings that are specifically designed for wet locations. When installing conduit in corrosive environments, it's important to use corrosion-resistant supports and fittings. This will prevent the supports and fittings from corroding and weakening. Use supports and fittings that are made of corrosion-resistant materials, such as stainless steel or PVC. When installing conduit in hazardous locations, it's important to use supports and fittings that are approved for use in hazardous locations. These supports and fittings are designed to prevent the ignition of flammable gases or vapors. Use supports and fittings that are specifically labeled for use in hazardous locations. In addition to the support requirements, the NEC also specifies requirements for securing conduit to boxes, cabinets, and other equipment. Conduit must be securely fastened to these items to prevent it from coming loose or being damaged. Use connectors and lockers that are specifically designed for this purpose. When connecting conduit to boxes or cabinets, be sure to use a bonding jumper to ensure electrical continuity. This will provide a low impedance path for fault currents and help to protect against electric shock. Remember that proper support and securement of conduit are essential for a safe and reliable electrical installation. Always consult with a qualified electrician or engineer before undertaking any electrical work. When dealing with electrical installations, especially in sensitive environments like schools, it's crucial to address the issue of electromagnetic interference (EMI) and electromagnetic compatibility (EMC). Electrical conduit can play a significant role in mitigating EMI and ensuring EMC. EMI is the disturbance caused by electromagnetic radiation emitted from electrical equipment, which can interfere with the proper functioning of other electronic devices. EMC refers to the ability of electrical equipment to function correctly in its electromagnetic environment without causing interference to other devices. Electrical conduit can act as a shield, reducing the amount of electromagnetic radiation that escapes from the wiring system. Metal conduit, such as RMC and IMC, provides better shielding than non-metallic conduit, such as PVC. The effectiveness of the shielding depends on the type of metal, the thickness of the conduit, and the quality of the connections. To maximize the shielding effectiveness of metal conduit, it's important to ensure that all connections are tight and that the conduit is properly grounded. Any gaps or discontinuities in the conduit system can allow electromagnetic radiation to escape. Use conductor fittings and connectors to ensure a continuous electrical path throughout the conduit system. In addition to shielding, electrical conduit can also help to reduce EMI by providing a low impedance path for ground currents. Ground currents can be a significant source of EMI, especially in systems with poor grounding. By providing a low impedance path, the conduit can help to divert ground currents away from sensitive equipment. To maximize the effectiveness of the grounding system, it's important to use a dedicated grounding conductor and to ensure that all equipment is properly bonded to the grounding system. The NEC provides detailed requirements for grounding and bonding in Article 250, Grounding and Bonding. In some cases, it may be necessary to use special types of conduit or shielding to meet EMC requirements. These may include shielded conduit, which has a layer of conductive material bonded to the outside of the conduit, or flexible metal conduit with a braided shield. The choice of conduit and shielding depends on the frequency and intensity of the electromagnetic radiation, as well as the sensitivity of the equipment being protected. Before selecting a conduit system, it's important to perform an EMI assessment to identify potential sources of interference and to determine the required level of shielding. This assessment should be performed by a qualified EMC engineer. In addition to the conduit system, other measures can be taken to reduce EMI and ensure EMC. These may include using filters, surge suppressors, and shielded cables. The most effective approach is to use a combination of techniques to address all potential sources of interference. Remember that EMI and EMC are complex issues that require careful consideration. Always consult with a qualified EMC engineer before designing or installing an electrical system in a sensitive environment. Moreover, consider the potential for harmonics in electrical systems, especially in schools with modern electronic equipment. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental power frequency, typically 60 Hz in the United States. These harmonics can cause various problems, including overheating of conductors, transformers, and other equipment, as well as interference with electronic devices. Electrical conduit can play a role in mitigating the effects of harmonics. By providing a low impedance path for neutral currents, the conduit can help to reduce the voltage drop caused by harmonic currents. The NEC requires that the neutral conductor be sized to carry the maximum unbalanced load, including harmonic currents. In systems with significant harmonic currents, it may be necessary to increase the size of the neutral conductor and the conduit to accommodate the increased current flow. Metal conduit provides better shielding against harmonic currents than non-metallic conduit. The shielding effectiveness depends on the frequency of the harmonic currents and the type of metal used. To maximize the shielding effectiveness of metal conduit, it's important to ensure that all connections are tight and that the conduit is properly grounded. In some cases, it may be necessary to use special types of conduit or shielding to mitigate the effects of harmonic currents. These may include harmonic filters, which are designed to block harmonic currents from flowing into the power system. Harmonic filters are typically installed at the service entrance or at individual loads that generate significant harmonic currents. When selecting electrical equipment for schools, it's important to choose equipment that is designed to minimize harmonic generation. This may include using electronic ballasts for lighting, variable frequency drives, volts for motors, and power factor correction capacitors for inductive loads. Equipment that is designed to minimize harmonic generation can help to reduce the overall harmonic levels in the electrical system. In addition to the technical considerations, it's also important to consider the cost of mitigating harmonics. Harmonic mitigation equipment can be expensive, and it may not always be cost-effective to implement. The decision of whether or not to mitigate harmonics should be based on a careful analysis of the costs and benefits. Always consult with a qualified electrical engineer before designing or installing an electrical system in a school. Electrical engineers can help to identify potential harmonic problems and to recommend appropriate mitigation strategies. Also, it is critical to address arc flash hazards in school electrical systems. Arc flash is a dangerous phenomenon that can occur when an electrical fault creates a high-energy arc. Arc flashes can cause severe burns, blindness, and even death. The electrical conduit can play a role in reducing the risk of arc flash. By providing a physical barrier between conductors and equipment, the conduit can help to prevent accidental contact that could initiate an arc flash. Metal conduit provides better protection against arc flash than non-metallic conduit. The metal conduit can help to contain the arc flash and reduce the amount of energy that is released. To maximize the protection against arc flash, it's important to use properly sized and installed conduit. The conduit must be large enough to accommodate the conductors and must be securely fastened to the equipment. The NEC requires that all electrical equipment be labeled with arc flash hazard information. This information includes the arc flash boundary, the incident energy level, and the required personal protective equipment, PPE. Workers who are working on or near energized electrical equipment must wear the appropriate PPE to protect themselves from arc flash hazards. The PPE may include flame-resistant clothing, gloves, and face shields. In addition to the PPE requirements, the NEC also requires that employees provide arc flash training to their employees. This training must cover the hazards of arc flash, the proper use of PPE, and the procedures for working safely on or near energized electrical equipment. The NEC also requires that employers conduct an arc flash hazard assessment. This assessment must identify potential arc flash hazards and determine the appropriate safety measures. The arc flash hazard assessment should be performed by a qualified electrical engineer. When working on or near energized electrical equipment, it's important to follow safe work practices. These practices may include energizing the equipment before working on it, using insulated tools, and maintaining a safe distance from energized parts. Always consult with a qualified electrical safety professional before working on or near energized electrical equipment. Electrical conduit is an essential component of a safe and reliable electrical system in schools. By following the requirements of the NEC and using proper installation techniques, electrical contractors can help to protect students, teachers, and staff from electrical hazards. The NEC is not a design manual, but a minimum safety standard. It is imperative to consult with qualified professionals during design and installation. Always use the latest edition of the NEC and local codes. Ensure that all electrical work is performed by qualified and licensed electricians.